100 kilonewton is applied to the beam. Determine the largest distance A for which the maximum tensile stress in the beam does not exceed 75 megapascal. Okay. The question I want to ask is this. How many moments are there? 1 or 2? Anyone? How many moments are we likely to see over here?
Looks like there's one along the y-axis.
Looks like there's one along the y-axis. Anyone else?
Looks like there's also. Oh wait, it's across from. Oh, sorry, that's only one.
Oh, there's two because maybe it's not acting at the centroid.
Right, we don't know yet. Okay, I don't know yet. Right, so we cannot. We can. That's where we have really to be cautious. Right, whether 1 or 2, it depends on the what. Depends. So the whether so whether do we have my or do we have m or mz or n, whether we have moment about y, moment about z is dependent, right? Dependent. Okay, dependent on the location of the what? Centroids. Okay, it all dependent on the location on the centroid. Now, centroid about the y-axis, about y for this case, and x-axis based on the transformation. Okay, so we have to be really cautious about it, and I'm glad you guys are seeing it. So we're going to quickly for this question, I'm just going to quickly identify the position of the centroid. Okay, we're going to quickly identify this position of the centroid. So we're going to follow based on the transformation that we see over there. So the transformation states that this is our x and this is our y, and then we are going to find out our rotation now z. Okay, sorry, for this case is whether I wrote wrongly. Okay, my apologies. Is it my or an mz? Okay, so we're going to sketch this out. Right, so this is our cross-section view. Right, so do we have another one? Beam below. Okay, so we are going to identify this is our y-axis. And based on what we are given over there, the next one, this is our x-axis. So we're going to divide this into 1 and into 2. Okay, so we want to find the centroid. All right, we want to find the centroid. We'll find the centroid. Along the y-axis. Right, the x-axis is straightforward. Yes or no? It's directly on the line, right? Because left is equal to right. So we want to find the centroid along the y-axis now. Okay, so we're going to have section. So I'm going to call this our section 1 and 2, and then the datum is going to be from the top, right? So section 1 and section 2, and we know that this is our width. And over here, this is our depth. Okay, So section 1, based on the geometry that we're given, the width is 100, the depth will be 20. So this will be equal to 2000. And then section number 2, the width is 60 multiplied by 20. So this is equal to 1200. And then the individual section position of the centroid from the datum. Okay, so this is equal to 20 divided by 2, 10. 20 for section 2, you have to take the 20 because it's from the datum drawn over here, plus by 20 divided by 2. So this will be equal to 30, right? So when you multiply them up, this is your omega d and y bar. So this will be equal to 20,000. And the next one is equal to 36,000. And then you finally do your summation. So this is equal to 56,000. And down here, this will be equal to 3,200. So your y bar, your global neutral axis is 56,000 divided by 32. So 56,000 divided by 3,200. So it's equal to 17.5 millimeters. Right, 17.5 millimeters. So i.e., the neutral axis, I'm going to draw in dark green now. All right. This is the position of the neutral axis. Okay. And then we have another position of the neutral axis over here. Right. And where the force is applied, the force is applied directly on the x-axis, right? And this is our P. So from here, we know that we will have, from this observation, we know that there will be a moment in the mx and my, okay, about mx and my, okay, about the x-axis and the y. So you have to be really be cautious, okay? You have to identify where the centroid is more important than anything else, okay? Are we clear? So be very cautious about this, okay? This is so-called very popular questions when it comes to student making mistakes, okay? Any questions so far? No? Right. So now we're going to start on a new topic. So this topic, okay, so we're going to start a new topic now. And this topic is one of the most confusing topic in structure analysis, okay? So we're going to look at shear stresses now. Okay, we're going to look at shear stresses. And if you were to look at your course textbook on the Beer and Johnson, so it's chapter 6.1 to 6.3. Okay. As I said, it's one of the most confusing topic in structure analysis. It's because there are rules that you have to apply, and these rules are critical. And I'm going to derive for you what those rules are. Okay. Now, before we go there, we are going to find out what is shear stress. So shear stresses are stresses acting parallel to the surface. Okay, so if I were to draw an element, so we're going to construct an element now. So we're going to construct a 2D element. So likewise, we have our transformation. So this is X, this is a Y. So we could construct element. So element, if we were to draw an arrow doing this now, right? This is the shear stress and the plane intersecting the x-axis multiplied by the direction of the force. Okay, so our the direction of the stress. So I'll write this out. The first subscript means the intersecting plane. And then the next one, the y over here that you see, the second subscript on the right, it means the stress acting direction. Okay, so for this case, over here, the top arrow over there is the shear stress acting on the plane intersecting the y-axis. Okay, so this plane over here that you see will intersect the y-axis, and the force down here, or the stress down here, is acting on the x-axis. And to achieve structure equilibrium, we know that the shear in xy is equal to the shear in yx. Okay, so on the other side, you have the stress acting on the other configuration. Right now, I'm not going to teach positive shear or negative shear yet. Okay, we'll leave that to later. But this is how the shear stress are acting. Now, if we were to view this now, if we were to view this on a 3D element now, so we're going to look at this in 3D element. Before I go into 3D, any questions so far? Nope, we are good. Okay, so if we look into 3D, right, we go into 3D. So in 3D, this is our transformation now. X, Y, and then we have our Z direction. Now we're going to draw a cube now. We're going to construct a cube. Right, so this is our cube. Right, so we are aware that this will be, this correspond, right, to our shear in the plane intersecting the x-axis multiplied by y-axis, and this will be the shear yx. Then I'm going to draw a different set of arrow now. Okay, I'm going to pick a different color. I'm going to draw a different set of arrow. So I'm going to draw to this set of arrow. Okay. So that's our shear, and that is equal to what? The shear on the plane that I'm writing on now, right? So that plane intersect the z-axis, right? And the vertical direction of the stress is y, right? So this is equal to shear yz. And then finally, the last one. So this is our shear direction, right? So on the face that I'm writing on, so this is shear in the plane intersecting the x-axis, and the stress is acting on the z-axis. So this will be equal to shear zx. Okay. So for the start, it looks confusing, but it takes getting used to it. So you need to know the first subscript. It defines the intersecting plane, and the second one is stress acting direction. That's it. Okay, for now. So I'm not, as I say, I'm not going to go into positive or negative shear stress yet. That will leave it for most circle. Okay. Now the next thing that I would like to highlight over here. So far, anyone, any questions? Are we okay? As I say, it takes time to absorb this. Anyone, any questions, please? No? Okay. So the next thing that we're going to look at